I'm very excited to present this project that I worked on with the programming languages and HCI researchers at the University of Washington. Two of them are actually here, Halden and Jeff. So when we're visualizing data, we have to go through this tedious process of picking a data set, such as this one here, this famous data set of the barley yields. Then we have to decide which fields do we want to actually visualize. Then we decide on aggregations or filtering to summarize or look at a particular subset of the data set. And then finally, once we went through this whole process, we can decide on the visual encoding of the data. For instance, here we create a bar chart that shows us the yield for each of the sites. Besides being very tedious, this process also requires design expertise. For instance, we have to decide what mark type do we want to use, or whether we should include 0 in the domain of this bar chart so that each of the bars, or the length of the bars, is comparable. And this design knowledge here is crucial. Visual design decisions can make the difference between having a misleading visualization or not seeing errors. For instance, in this data set here, we can only see that the site, for the Mars site, that we swapped the years when we visualize it as a line. In the left chart, you have to decode the data, whereas in the right chart, your fast object recognition system can kick in, and you can immediately see what's wrong with the data. So researchers have developed systems that help us encode these design rules that we're applying in order to make this process that's usually tedious and requires design expertise easier. And these are called automated visualization design systems. These are systems that use design guidelines to support users to create good visualizations. Supporting here means that there's a human and a machine working together. We're building a visualization assistant. We're not trying to replace the designer, but working with them and help them. These systems also don't necessarily have to create the best visualization, but they have to find a good one so that it can help the analyst kind of go to the next step. It can also never be perfect because the system doesn't have complete information. These systems that started dating back to the 1960s usually take in some incomplete specification that's coming from some user interface or maybe a program, then synthesize a graphical design from that, and then finally render it. As I said, it started in 1986 with Jock McKinley's APT system, but it continues to just a few years ago. What's important about these systems to keep in mind is that they had to re-implement a lot of the design rules that are used. They couldn't use a knowledge base or something that was implemented in a previous system, but instead they had to look at the papers or look at how the system worked and then re-implemented design rules. So to address this problem, we created a system called Draco. And it is a formal model that represents visualizations as a set of logical facts and design guidelines as a collection of hard and soft constraints over these facts. And what we can do with this knowledge base of visualization design is we can build reusable and extensible models that can then build into new systems. And this helps us increase developer productivity. Another very exciting thing is that we can start to automatically reason about this knowledge and build systems that can be very smart or understand what our knowledge about visualization is. So in this talk, I'm going to show you how we model visualization design in Draco and of what is the underlying representation that we use. Then I'm going to tell you how we encode visualization design rules as constraints. And then lastly, I'm going to show you how we learn trade-offs among rules using machine learning. So let's start with the representation. As I said, in Draco, we represent visualizations as a set of logical facts and design knowledge as constraints. So for instance, for this bar chart here that you've already seen, to represent it as logical facts, we have something like this here. We say the data set is the barley data set, the mark is bar, and we have two encodings. One continuous encoding that shows the aggregate sum, and Y encoding that's categorical and shows the site. So this is how we describe visualizations. This maps to Vega Lite if you're familiar with it. Then design knowledge is expressed as constraints, and we have 3 sets of constraints. The first one are about the domain of the attributes that you've just seen in the representation. For example, we can say that the mark of a chart should be one of bar, line, area, or point. And we express this in our formal language like this. We say the mark is an instance or an element of one of these items in this set, with bar, line, area, and point. In the actual system, we implemented a few more mark types, but for illustration purposes, I will use a constraint subset. We did something similar for the other attributes that we have in our specifications. So as I said, we had mark, but we also have channels, fields, types, and so on. We also have a language to express other input from the user, for instance, about their task, or information about the data set, the data schema, which is also encoded as these logical as these sets. Then the second set of constraints we have are integrity constraints. And what they ensure is that the combination of attributes makes sense. So for instance, we can say only continuous fields can be aggregated. In our language, we express it like this. And this, you can read this as, for all encodings, if the encoding has an aggregation, then the type of that encoding has to be continuous. And this is a constraint that cannot be violated, because you can only aggregate continuous fields. And we have a set of these constraints. Here's one that says that if you want to use the chart channel, you have to use the mark point, or a bar chart needs an X or a Y encoding. The third set of constraints are preferences. And these are constraints that allow us to have exceptions to these rules. So for instance, we can have this rule that says, we prefer to include 0 in the domain, so that we don't mislead people with the length of the bars. You're familiar with this for these bar charts. In our language, we express it similar to the normal constraints. We say for all encodings, the encoding should use 0. The T here means that it has to be true. Note that there is this 5 at the beginning. And this is the cost that we're using, or that gets incurred if the constraint is being violated. And we call these constraints soft constraints. As you might notice, this constraint is not quite what you want. You don't always want to include 0. So you can make it more concrete and say, let's only include 0 for continuous fields. So we updated this constraint to also incorporate this more specific, or where this rule actually applies. Okay, so to recap, visualizations as logical facts and 3 sets of constraints. Where do these constraints come from, you might ask? Well, we designed them based on CompassQL, which is the recommendation engine behind Voyager and Voyager 2. And we developed the set of constraints that we're using in this system over multiple years. Back then it was implemented in an imperative JavaScript system, and we ported them to this logical language. So what do we do with this? There's actually a bunch of things we believe we can do with having this formal representation of knowledge and visualizations. You could recommend visualizations, compare models, enumerate design spaces, but in particular the one I want to talk about here is automated visualization design. And the way we formulate it in Draco is that we model automated visualization design as finding a model that optimally completes the constraints. Let's go through what this looks like. Think back to the visualization that we heard earlier. The user might say something like, I want a visualization that shows the site and the yield from the barley data set. This is a partial specification of what the user actually wants, or what the output visualization should be. And so the system will automatically complete that. The first thing we have to do is translate this natural language query to a set of constraints, or these facts here. So the data set is barley, and we need 2 encodings, one for site, one for yield. Then we add to these facts here the constraints that we've defined earlier, the domain, the integrity, and the preferences. And then we use a constraint solver to then synthesize from that a complete specification, which we can then render. The weights here allow us to do probabilistic reasoning. The solver that we're using is called Chenglong, which is an off-the-shelf solver. Let's look at what this looks like. Again, here's the barley data set, and if we say we only want to show the yield, we get this tick plot. Under the hood, what we actually get are multiple visualizations, but I'm always going to just show you the first one but in a real system you might surface more than just the best one. If we add that we want the yield encoding to be discretized, then Draco automatically adds a count here to create this histogram, because otherwise we would have overlap when it are on top of each other. And the reason why this works is because we have these constraints with associated weights. And the cost of preventing overlap, which is the last constraint here, by adding an aggregate is less than the cost of adding a count encoding, which are the first two constraints that you see here. Let's go back to the tick plot from earlier and add another field, another encoding where we want to visualize the site. Now we get this tick plot that's broken down for each site. If we then force Draco to switch to a bar chart, Draco again automatically prevents overlapping by adding an aggregation here. Similar to before, the cost of switching here from a tick to a bar is only 1, whereas the cost of not having the cost of having overlap would be 3. So the overlap is prevented again. So as I said, we implemented a lot of the constraints from CompSQL. One huge advantage was, though, that 20 lines of code that were in CompSQL resulted in a single line in our formal language, because the declarative approach is more expressive. We have about 70 constraints here and about 110 soft constraints. So you can imagine how large the code was in an imperative version. And in the future, we want definitely more. Also, in CompSQL, we had to have additional scoring logic, which we could outsource to the solver in our logic implementation. So this is awesome, but you might say, well, what about all these weights for the soft constraints? Where did those come from? And the way we approach this is that we, in addition to this kind of classical AI approach of designing and modeling knowledge, we use machine learning to get the weights. So how does this work? Well, for machine learning, you need 3 things. First thing is features. What are actually, what is the space that you work over? And what we use are the violations of soft constraints. Then, training data, we used pairs of ranked visualizations. And then a learning algorithm where we just use a simple linear support vector machine. You can see the formula there if you're familiar with it. So how do these violations as soft constraints work as features? Let's look at the example from earlier again, where we had the 2 bar charts, one with 0, the other one without. The chart on the right here violates an additional constraint. The constraint that if the encoding is continuous, we should include 0. And so this has a higher cost. One cool thing about this is this approach of using violations of soft constraints as features is that we can model nonlinear relationships, even though our learning system is a linear support vector machine. Okay, now that we have one of these examples here, let me walk you through the process of actually learning. What we do is we take these pairs of visualizations and convert them to their feature vector representation. Remember, each element is the number of violations of the soft constraint at that location. So the length of the vector is the number of soft constraints. Then what we try to do is to separate these vectors as much as possible. So we're taking the distance between those and weighting them and try to maximize that. And what we're doing is not just for one example, but for all examples at once. And so this way we can learn the weights, which we then just feed back into the system. So how well does this work? To evaluate it, we looked at Draco CompSQL, which doesn't have task awareness. We tried to build a system that is actually aware of what is the user's primary task. And we have these 2 tasks, value and summary. And one you want to look at a particular value, and the other one you want to look at a summary. And no surprise, we get the same visualization from the system without task awareness. And so then we took the system, ignored the weights, used 2 user studies from Yang and Bahadur to extract these pairs of visualizations, and then learned from that and achieved about 96% test accuracy on an unseen data. The normal version achieved around 65%, so a little bit better than chance. And then as a result, we got a task-aware Draco system. And so this demonstrates that this machine learning approach works for learning visualization design. And it learned these relationships that exist in the data. We're very excited about taking this system and applying it in a bunch of domains and building systems on top of it. A few future directions that we're thinking about are using this for automated design of interactive dashboards rather than just these single static charts. We also want to integrate it into plotting APIs to make it easier for people to actually use this design knowledge. And lastly, we want to build tools to browse, update, and compare these knowledge bases that we have in Draco. One example you can see here on the left, which is an online editor that we've developed that where you can try Draco without installing anything. What's exciting about this is that we can evaluate the impact of new perceptual models and test what we know and understand its implications. If you think this is exciting, please let me know. Just send me an email or message me on Twitter. We have a Draco meetup where we're going to talk about, or we're going to get people together who want to use Draco in future work. So on Thursday at 1 p.m. we're going to meet at a restaurant. If you want to come, please let me know and I can invite you to that as well. So in summary, Draco is an extensible and adaptive knowledge base of visualization design, which enables a few new applications, which enables us to do things like automated visualization design, formal reasoning. It can be a shared resource for us as a visualization community to share what we know and accelerate the knowledge transfer from us to the people in the field. Everything I've talked about is open source. You can go to this domain and check it out. We also just published a blog post yesterday where we make this approach a little more accessible. I'm also graduating, so if you're hiring for academic positions, please come and talk to me. And if you have questions, let me know now.